Hello, this is Richard Hammack's Calculus 1. We are in part 4 of the course on applications of derivatives. This is Lecture 36A, Linear Approximation. Before beginning, let me give you an overview of part 4. I'll remind you of what we've been doing and where we're going. In lectures 30 through 34, the topic was maxima and minima, using derivatives to find largest and smallest values of functions. And then in lecture 35, we discussed the mean value theorem, which, if you've read the proof, comes out of the theory of maxima and minima. Today we'll begin lecture 36A on linear approximation. This is all about finding the best fit to a nonlinear function by a linear function. It's not the most important thing you'll do in Calculus 1, but as you go on, and if you take Calculus 2, it'll take on greater shades of meaning. Then in lecture 36B, we're going to apply linear approximation to derive a technique called Newton's method, and it's a means of using calculus derivatives to solve equations that can't be solved by other means. Finally, a three-part lecture, lecture 37, will be on what's called L'Hopital's rule. And the basic idea here is that you're using derivatives to evaluate limits, applying derivatives to limits. So the overall theme in part 4 of the course is applications of derivatives, using derivatives and applying them to other problems. But let's start today's topic, linear approximation. This is related to a problem you've done many times. Find the equation of the tangent line to the graph of y equals f of x at a point a, f of a. And there's a picture for this. Here's your function f of x. Pick an x value of a and look at this point a, f of a on the graph. And there's a tangent line there. So what we want to do is find the equation of this tangent line. Now that's a straight line, so we're going to get a linear equation. And the way we've tackled this problem in the past is we started with the point slope form, y minus y naught equals m times x minus x naught. And our point x naught, y naught is a, f of a. And of course our slope m is f prime of a, the slope of the tangent line. So plugging all that information into the point slope formula gives y minus f of a equals f prime of a times x minus a. And solving for y, we get y equals f of a plus f prime of a times the quantity x minus a. This is a linear function. You could distribute that f prime of a into the parentheses and collect like terms and get this into the form of y equals mx plus b. But we're going to leave it in this form for convenience. Note that f of a, f prime of a, and a in this equation, they are all constants depending on f and a, and x is the only variable. So this is definitely a linear function. We're going to call this linear function L of x. So f of x, it might be a nonlinear function, but L of x, which is f of a plus f prime of a times x minus a, the equation of that tangent line, that's a linear function. And the thing about this linear function, L of x, is that at least if x is close to a, it's a really good approximation to f of x. If you plugged in an x to f, you'd be way up here on the graph of f. And for all intents and purposes, that looks like virtually the same as plugging x into L. You can see here that f of x is approximately equal to L of x, as long as x is near a. So we're going to take these observations and codify them into a formula. We call this function L of x equals f of a plus f prime of a times x minus a, the linear approximation to f at a. And as we said, f of x is approximately equal to that linear approximation for values of x that are sufficiently close to a. So the way to look at this is L of x is the best fit to f of x by a linear function at x equals a. You can't get a better fit to this nonlinear function by a linear function than this exact function L of x at that point x equals a, because it's the tangent line. Here's an example, and up at the top I have a reminder of that approximation formula. Let's find the linear approximation of the function f of x equals the fifth root of x at the number a equals 32. So here's a picture of the situation. You've got your function y equals the fifth root of x, which looks something like this. And we're looking at an x value of 32. It's right there. F of 32 would be the fifth root of 32. And let's see, 2 to the power of 5 equals 32. So the fifth root of 32 is easy to compute. It's 2. So this is the point 2 comma 32 right there. And L of x is the equation of the tangent line to the graph of f of x at this point. And you can see it here, and it's a really good approximation to the function near x equals 32. You can't even tell those graphs apart for those values of x. And sure, you get noticeable deviation later, but right here, the linear approximation, it's the best fit to the function f of x at that point by a straight line. So our function is f of x equals the fifth root of x, and we want to use this approximation formula to compute L of x, and there's an f prime in there, so we've got to find the derivative of f. So let's write that as x to the 1/5, so we're ready to use the power rule. So we compute f prime of x as 1/5 x to the power of minus 4/5, which simplifies to 1/5 fifth root of x to the power of 4. So let's work out our linear approximation. We know that for values of x near 32, f of x is approximately equal to L of x, and L of x is f of a plus f prime of a times x minus a, and you see that right here with a equals 32, f of 32 plus f prime of 32 times x minus 32. We're just plugging 32 in for a into our approximation formula. So f of 32 is remember f is the fifth root of x, so f of 32 is the fifth root of 32. Then f prime of 32 would be this expression with 32 plugged in for x, and we multiply it by the x minus 32. Now the fifth root of 32 is 2, and let's see, the fifth root of this 32 is 2 to the power of 4 is 16 times 5, that's 80. So we get 1/80 times the x minus 32. So this simple linear function, that's our L of x. F of x is approximately equal to this linear approximation to the function by this linear function. And there we have it. You can plug in values of x that are close to 32, and you can quickly compute an approximation to a function value, f of x. So as an example, think about the fifth root of 33. 33 is very close to 32. We're taking f of 33. 33 is about right there in this picture. And if you were going to compute the fifth root of 33, or f of 33, f of 33, for all intents and purposes, that's just L of 33. I mean, sure, it's going to be a little bit of difference, but you can barely tell it here. So the fifth root of 33 is approximated by 33 plugged in to L of x. So 2 plus 1/80 times 33 minus 32, and that's just 161/80, which works out to be 2.0125. So that's an approximation to the fifth root of 33. And if you take a calculator and work that out, you'll get something like the fifth root of 33 is 2.012346661 and so on. We're truncating there. But you can see that this linear approximation, it got the fifth root of 33 to 3 decimal places, which is pretty good. So the idea here, again, is that we have approximated a complicated nonlinear function with a simple linear function. In conclusion, we have derived a linear approximation formula. L of x equals f of a plus f prime of a times x minus a is a linear function. Its graph, which is a straight line, is the best fit to the graph of a nonlinear function f of x at x equals a. And as we noted, f of x is approximately equal to L of x for x that are near a. So as I said, this is not the most important topic in calculus. It's not something you're going to be using every day, but it's still a significant paradigm to be aware of. Next up, in Lecture 36B, we will apply linear approximation to solving equations and derive what's called Newton's method. I'll see you then. Goodbye.